Okay. So we have completed the study of regular stem problem. The next two topics will talk about other problems related to the regular stem problem. So the first one is like this. If we change the boundary condition of a regular stem problem to YA equal to YB and Y prime A equal to Y prime B. Right, so we change the boundary conditions. Alright, to this without changing the other assumptions like the community of the coefficient polynomials like P of x, P prime of x, Q of x, and R of x, as well as the positivity of P of x and R of x. Alright? So where but still assume that P prime, Q are real valued continuous function. Okay, continuous functions AB and P of x greater than 0, R of x greater than 0 for all x in the defining interval. Alright? With an additional, so with an additional property, PA equal to PB. Right? So there are actually there are two changes. First of all, the first one is that we change the boundary conditions, into this boundary conditions here. The second change is that we add an additional requirement that P of A equal to P of B for the coefficient functions P of x here. So that I highlight them. So this one. And this one. Alright. Then we call this new problem as a periodic stem linear problem. on AB. Okay, so right, so now so for this problem, we let V sub P consist of O complex over real valued functions U on AB such that 1 U is continuous differentiable. On AB. Second, the derivative of U is absolutely continuous. Okay, on AB, and which implies that the second derivative U double prime of x of U of x exists for almost all for almost all points x in AB. Okay, all right, and the third point is that the same derivative, since it exists for almost all points x in AB, so that this derivative is in L2 space here, and the first one, U of x, satisfy the two periodic boundary conditions. Okay, means i.e. UA equal to UB and U prime A equal to U prime B. Okay, so so that so we call this one as periodic boundary conditions. Okay, because that will require the solution of the Stern-Liebler equation, satisfying that at the two endpoints they have the same value, and also at the two endpoints the derivative of the solution has the same value. Okay, so we call them as periodic boundary conditions. Yeah. Right, so okay. So again, it can be verified that V sub P is a vector subspace the L2 space. Okay, and in this case, okay, define a linear transformation L from V sub P to the L2 space. Okay, so for every U here, it goes to LU. Okay, and with L of U, okay, that is the function at 1 over R, alright, and minus P times E prime minus Q of U, okay. Okay, so you can see we have these linear transformations. So it sends a function in V sub P to a function in the L2 space here. Okay, and this linear transformation L will be which will be called a periodic Sturm-Liouville operator. Okay, associated with a periodic Sturm-Liouville problem. On AV. Okay, alright. So now corresponding to associated with the previous periodic Sturm-Liouville problem, we establish a linear transformation L from V sub P to the L2 space. Okay, you can see that. All right, and so that so such an operator L is still self-adjoint. Okay, with respect to the weighting function of x, i.e. that U are equal to V are equal to U L of V R, i.e. the inner product L of U V is equal to for all U V in V sub P, right? This is because that the Lagrange. So Lagrange's identity, right? In say here in the proof of, I think, in the proof the Lagrange identity in the proof of theorem 11.5.8, where we proved that a regular stem-Levy operator is self-adjoint, right? And so that the Lagrange's identity in this theorem, which is that L U V R minus U L V R equal to P of X and U of X V prime of X bar minus U prime of X V of X bar B. Okay, so we have this Lagrange identity. Okay, we have this Lagrange identity. Okay, right. So this Lagrange identity has the right-hand side. So right-hand side is here. Okay, so right-hand side, as you can see, okay, so right-hand side P of X, so B, okay, and the U B V prime B bar, okay, minus U prime B V B bar, okay, minus P of A, okay, P of A and V UA V prime A bar minus U A prime V A bar. Okay, so this is the right-hand side here. Okay, but as we know, since PB is the same as PA, right? So that we can see here. So PB is equal to PA, and now since so we can do that. We know the data here. As for the periodic problem, we know PA equal to PB, and also UA equal to UB, okay, and U prime A equal to U prime B, right, and VA equal to VB, and V prime A equal to V prime B. Okay, because U and V are functions in V sub P. Functions in V sub P satisfy the two periodic boundary conditions. So we have that. So that so you see PB is equal to PA, and UB is equal to UA. Okay, and V prime B is equal to V prime A. Okay, and U prime B is equal to U prime A, and VB equal to VA minus PA, UA, V prime A bar minus U prime A, and VA bar here. Okay, and so you can see this product is the same as this product, so you get 0 here. Okay, so the right hand side, equals 0, right? And so of course that this difference is 0, right? And so we have the equality here. Okay, so this shows that. A periodic Sturm-Liouville operator still self-adjoint. Okay, still self-adjoint. Right, so similar to theorem 11.5.8, right? A periodic Sturm-Liouville operator is also self-adjoint. Okay, and also with a similar. So with a similar proof as in theorem 11.5.c. In this theorem, we prove that the eigenvalues of a regular Sturm-Liouville operator is real. Okay, so with a similar proof as in this theorem, any eigenvalue, alright, so any eigenvalue of a periodic periodic Sturm-Liouville operator, okay, periodic, if it exists, okay, if it exists, it's a real number. Okay, and with a similar proof as in theorem 11.5.1, if phi I and phi j are two eigenfunctions of a periodic Sturm-Liouville operator corresponding to distinct eigenvalues lambda I and lambda j, respectively. We have that the inner product with respect to the weighting function R, okay, which is just this weighted integral R is 0. So I, phi I, and phi j. orthogonal. Okay, with respect to the weighting function of x. Okay, so a periodic stability operator share several property with a regular stability operator, such as first they are both self-adjoint. Second, any eigenvalue of either operator, if exists, okay, must be a real number. And for either operator, any two eigenfunctions corresponding to distinct eigenvalues must be orthogonal with respect to the weighting function of x. And we didn't mention a property we proved for a regular Sturm-Liouville operator, which is theorem 11.5.b. In that theorem, we show that any eigenvalue of a regular Sturm-Liouville operator, if it exists, must be non-degenerate, which means that eigenfunctions corresponding to an eigenvalue of a regular Sturm-Liouville operator must be related linearly. Okay, so but this property cannot be shared with any periodic. It's not true for all periodic Sturm-Liouville operator. Okay, right. So that means that an eigenvalue of periodic Sturm-Liouville operator may be degenerate. All right. So let's take an example to show this. So consider so consider a periodic Sturm-Liouville problem y double prime plus lambda y equal to 0 with y minus pi equal to y pi, and y prime minus pi equal to y prime pi. Okay. Right. The interval. Okay. Now, all right. So in this periodic Sturm-Liouville problem, we know the P of x is the same as the weighting function, which is a constant function 1. And we know Q of x is equal to 0 for x in minus pi to pi. All right. And it's a periodic Sturm-Liouville problem because not only we have these two periodic boundary conditions, but we also that we know PA, P minus pi equal to P of pi equal to 1, because P function is a constant function. Okay. Yeah. Okay. So now we now show that solve this is a periodic Sturm-Liouville problem. Now, so if lambda is minus mu square, okay, with positive, which means that if lambda is a negative number, then there is no non-trivial problem as solution, as we have done in the previous examples there. Okay, because we consider in the previous two examples, example 11.5, 11.5.2, we have the same differential equation, okay, but with different boundary condition there. Okay, so but we can still check about that. You can easily to check that when lambda is negative, there is no non-trivial solution. But for lambda equal to 0, all right. Now a general solution of the Stern-Liebowitz equation. Right, so for this is Stern-Liebowitz equation, this one, it's it's y of x equal to c0 plus c1x here. Right, so this is a general solution. Now we apply the two periodical boundary conditions. So we must have here y minus pi, which is c0 minus c1 pi, which must be equal to c0 plus c1 pi, which is y pi. Okay, and also we know that this implies y prime of x equal to c1. Okay, and the y prime minus pi, which is equal to c1, which is equal to y prime pi. Okay, because the derivative of this is general solution is equal to c1. Okay, so automatically the second boundary condition is satisfied here. Right, and so for that, so from here, this boundary condition implies that we can cancel c0, so we have 2 c1 pi equal to 0, which implies c1 is 0. Okay, so we know c1 is 0, and the c0 can be arbitrary. Okay, so that once lambda 0 equal to 0, defined to be 0, x an eigenvalue, because we have the non-trivial solution. It can eigenvalue of this periodic Stern-Liebowitz problem. Okay, and there is only one. There is only one. Only one linearly independent eigenfunction. So, and we memorize it so that this will be 1 over square root of 2 pi. Okay? Right. Which is memorized. Okay, so it's 1. So you can see this eigenvalue 0 is non-degenerate because there's one unique eigenfunction up to a constant. Okay, so So that so this is the first one. Now for lambda to be positive with mu. Okay. Now a general solution. So a general solution of the Stern-Liebler equation is here. Is y of x equal to a cosine mu x plus b sine mu x here. Okay. All right, and so the derivative. So the derivative becomes mu a minus, sorry. So it's minus mu a sine mu x plus mu b cosine mu x. All right, here. All right, and so by the two periodic boundary conditions, so we know that so y pi is equal to a y minus pi, sorry. So a cosine minus pi mu, okay, plus b sine minus pi mu. Okay, this one must be equal to a cosine pi mu plus b sine pi mu, because this is equal to y pi. Okay, and y prime minus pi was here, x equal to minus mu a, and sine minus pi mu plus mu b cosine minus pi mu. Okay, that's equal to minus mu a sine pi mu plus mu b cosine pi mu, which is equal to y prime of pi here. So we have two equations. We have two equations now. Okay, so we have two equations. And we look at these two equations, we see that. Okay, so now we apply that, because cosine is an even function, sine is an odd function. So we have so this is implies as a cosine pi mu minus b sine pi mu equal to a cosine pi mu plus b sine pi mu. So the first equation is here. And the second equation gives us the mu a. So they have vectors mu, right? But mu is positive, so we can just cancel the common factor mu here. So we have a minus a. So sorry. So minus, so we got a sine pi mu plus b cosine pi mu equal to minus a sine pi mu, right? And here is plus b cosine pi mu here. Now the first equation, so look at that. These two terms can be cancelled each other, okay? And the same, we can cancel each other. So you can see that b 2b sine pi mu must be 0. Okay? So, so which means that we just cancel B, 2, right? So B times sine pi nu equal to, sorry, not nu. Okay. Equals 0. And here, similarly, we have A, okay, and sine pi nu equals 0. Okay, so we have these two conditions. We have these conditions. Now, if sine pi nu is not 0, then then A and B, both of A and B are zeros. If this is non-zero, all right. So that this implies that we do not. So we do not have any non-trivial solution. Okay. So if nu here nu is a positive number such that sine pi nu not equals 0, then we have no non-trivial solutions. Okay, and so to have a non-trivial solution. To have non-trivial solutions, okay, we must have that sine pi nu must equal 0. Okay, so this is so that if this is 0, of course, both equations are satisfied, and the A and B can be arbitrary, right? So to have a non-trivial solution, we must have this one, okay, and this implies that nu, okay, nu is equal to 1, 2, 3, etc. So nu must be a positive integer because nu always here is positive. Okay, so nu must be positive integers. All right. Okay. And for each, okay, so for each lambda n defined to be n square, n is any natural number, okay, they are, okay, so in here A and B can be arbitrary, right? So that we have a degree, 2 degrees of freedoms, so they are exactly 2 linearly independent eigen functions. Okay, so the functions okay, so phi n1 x cosine nx, but we can memorize it, right? So that 1 over square root pi, because this is a memorized eigenfunction, and phi from 2 is 1 over square root pi and sine nx. Okay, so which normalized. Okay, so you can see that for this particular periodic stem behavior problem, that we have eigenvalue 0 and eigenvalue the square of any positive integers. And as we see here, eigenvalue 0 is non-degenerate because it has only one linearly independent eigenfunctions, a constant function here, and which is normalized. And for eigenvalue which is equal to n squared, where n is any natural number, then for such eigenfunction is degenerate, and it has two linearly independent eigenfunctions. Okay, and so here a cosine function and sine function, they are normalized. So that's, so you can see 2 pi cosine x sine x cosine 2x sine 2x and etc. Okay, so this is also normal eigen system, okay, corresponding to system of this periodic stem behavior problem. Okay, and this is exactly the trigonometric eigensystem. Okay, we used at the beginning of this chapter. Okay, so this is the trigonometric, right? But we normalized the functions in this eigensystem. So this is also normal. Okay, this is also normal eigensystem there. All right, and so now in theorem 11.5 and point D, we give the distribution of eigenvalues of a regular stem behavior operator, and so now we listed the next theorem give us a distribution of eigenvalues for a periodic stem behavior operator. So the eigenvalues, of periodic, okay, the eigenvalues of a periodic stem behavior operator, okay, from an infinite increasing sequence number 1, alright, very interesting. Number 2, number 3, number n, and as n goes to infinity is infinity. Okay, so this shows that there is a smallest eigenvalue, and this smallest eigenvalue is non-degenerate. Okay, it's non-degenerate, but all other eigenvalues, okay, all other eigenvalues may be degenerate. Okay, so that the number 2 and number 3 may be equal. Alright, so that this eigenvalue is degenerate, etc. Okay. Alright, and so that the first eigenvalue, number 1, is non-degenerate. Right. And the number of linearly independent eigenfunctions corresponding to an eigenvalue number n is equal to the eigenvalue number, okay, is equal to the number of terms lambda is repeated in the above listing. Okay, in the above listing. So you can see you have so this is the about the degeneracy. Of course, if in the listing for some eigenvalue it only repeat just once, appear once, then that eigenvalue is non-degenerate as the first, the smallest eigenvalue. Okay. Okay, so that is the about the distribution of eigenvalues of periodic Stern-Liouville operator. Okay. Right. And of course that as we have shown, have indicated that for any two eigenfunctions corresponding to distinct eigenvalues of periodic Stern-Liouville operator, they are orthogonal to each other, right? They are orthogonal to each other. And for a degenerate eigenvalue, we have more than one linearly independent eigenfunctions. Okay, and in linear algebra, there is a procedure. Okay, the procedure we call the Green-Schmidt orthogonalization procedure. We can turn this linearly independent eigenfunction to orthogonal eigenfunctions. Okay, so suppose that for a particular eigenvalue lambda, there are 3 linearly independent eigenfunctions. Then we can, starting from these 3 linearly independent eigenfunctions, we can end up with 3 also normal eigenfunctions. Okay. Okay, so all right, so let's say that since we can since we can obtain orthogonal eigenfunctions, so say okay, orthogonal orthogonal eigenfunctions from linearly independent eigenfunctions corresponding to degenerate eigenvalue lambda of with multiplicity of periodic Sturm Liouville operator by a procedure called Graham-Schmidt. Okay, also called normalization procedure. We can form also normal eigen system. Okay. Phi n from 1 to infinity with respect to the weighting, with respect to the weighting function of x. Okay. Right. So now, as a regular Sturm-Liouville operator, we have an orthogonal as a normal eigensystem. Okay, we can have an orthogonal eigensystem, and in this for a regular Sturm-Liouville operator, each eigenfunction in this eigensystem corresponding to distinct eigenvalues, because every eigenvalue is non-degenerate for a regular stem-derived operator. But for a periodic stem-derived operator, an eigenvalue may be degenerate, so that they may have more than one eigenfunctions in this eigensystem corresponding to the same eigenvalue. Okay, but that's okay. We still can construct an eigensystem. All right. So now with this eigensystem, we will raise up the convergence and representation problem as for a regular stem-derived operator. Okay. So now for any function in the Hilbert space, okay, the series, so we can establish a series C sub n phi n x with the coefficient Cn to be the projection of the function to the direction, okay, along the phi n eigenfunction. Okay, so this is okay. So this is series. Okay, this series is called the periodic generalized Fourier series generated by F, right, with respect to no isomorphic system, no isomorphic eigensystem. Phi sub n and from 1 to infinity. Of the periodic stem-derived problem. Okay, but we know that before we answer the convergence and representation problem, okay, of this series, then we should know that the series, okay, summation and from 1 to infinity Cn phi n x, okay, has the same value okay at x equal a at both m, as both end point, x equal to a and x equal to b, if converge. Okay. Right. So if the series converges, then the sum of the series has the same value at x equal to a and x equal to b. This is because that the eigen phi n a, the eigen functions, all right. So the eigen functions is in VP, okay, and so that it satisfies for n. Okay, so it satisfies the boundary conditions. Okay, actually, this is just one. Right? They said satisfy the two periodic boundary conditions. Okay, so so this is periodic questions we have. So now we state the representation theorem of periodic generalized Fourier series. Okay, so representation theorem of periodic generalized Fourier series. Right. So again, let F be piecewise continuous. Okay, on AB, and have a piecewise continuous derivative on AB. First, the periodic generalized Fourier series summation f from 1 to infinity Cn y and x generated by f with respect to also normal eigensystem Yn from 1 to infinity of periodic stem-Liouville problem on AB. Okay, so this series will converge to what? To the half of the left-hand limit and the right-hand limit at each x in the open interval. Okay? And the two half of the right limit at A, because A is the left endpoint, so it has only a right limit plus the left limit at B. Okay, so we go to the average at x equal to AB. Okay, so this shows that this general Fourier series always converge. Okay, converge to all any points in the Minkowski interval. Okay, but as we know, if it converge, then the value, the sum of this series has the same value at x equal to A and at x equal to B. Okay, So they must converge to the same value at x equal AB. And what is that value? And very interesting, it's just the average of the arithmetic average of the right limit of f at the left endpoint A, and the left limit of f at the right endpoint B. Okay, so that is the situation. Okay, the second thing, if in addition f is continuous on AB and FA equal to FB. Okay, so that then the periodic then the periodic generalized Fourier series generated by f. Okay, so this is converges uniformly to f of x on AB. Okay, so that we have this. Right? So it's very interesting. Right? So that's we have that. We will give a correction. Excuse me. Okay, so this is the about the representation. Okay. So now we consider regular string-Liouville problem as well as periodic string-Liouville problems. Now there are some related problems. Okay, there are some other string-Liouville problems that we call singular. Okay. Now, so here, now, so this, let me see, up to now, we have often assumed that string-Liouville equation, okay, okay, so a string-Liouville equation, as we discussed at the beginning of P of x y prime plus q of x plus lambda r of x y equals 0. Okay, so in such a a standard equation. Okay. Okay, so we assume that standard equation here is regular on a finite closed interval AB. i.e., we have assumed that P prime, Q, R are continuous on AB, and we have assumed that P of x greater than 0 and R of x greater than 0 for x in AB. Okay, so we have shown that the equation, okay, is on a finite closed interval, and we assume that they are continuous, and P and R are positive, okay, on the whole finite closed interval here. But they are, however, they are equations, okay, in which some of these conditions are not satisfied. For example, the standard equation may be defined on an infinite interval, right? Maybe interval, or only for an open interval example like that. Okay, and then we may not have that P or X always positive. Okay, so that will cause some problem, okay, to the discussion. Okay. Okay, so we will consider in the rest of this section. We will consider those problems. So now a stem Liouville equation, a standard equation is called singular. Okay, it's called singular on an interval I. If I is R, so if I is the whole real number, or semi-infinite. Okay. Right. Or, so this first one, the interval, instead of the finite closed interval now, I is the whole real line, or semi-infinite. Okay? Or semi-infinite. Or if the functions P, Q, R satisfy the conditions so the function PQR satisfies the conditions stated earlier for a regular stem-Liouville equation, stem-Liouville. On the finite cluster interval, AB, except at least one of this function fails to satisfy the first one then at one or both of the boundary points A and B. Okay? Right, so for example, that the boundary, okay, so for example, that the P of X is not positive at X equal to A, right, for example, for P not always positive for all X in the defined interval, okay. Okay, and instead, suitable boundary condition will be imposed. Okay, so the purpose is that this self-adjoint property of the associated stem-Liouville operator L will still hold true. Right? So we want that we impose equal to i.e. over the interval okay, so this must be true for all UVI in suitable vector space. Of functions. Okay, so we still want to impose the suitable boundary conditions so that the corresponding steam behavior operator L is a set of joint. Okay, so that we want this property to be kept. Okay. Okay, and so a singular stern wheel equation. So at an interval I together with such suitable boundary conditions is called a singular stern wheel problem. Okay. Okay, so let's take a look at an example. So this is the first example in this section. So we consider the Legendre equation. We learned the Legendre equation in ODE. So this is 1 minus x squared. Okay, and y prime plus lambda y equal to 0, and x is in minus 1 to 1. Okay, so x is in this open interval. Well, lambda is a parameter. Okay, that's a parameter. And we have learned how to solve these Legendre equations, and we know that for which parameter lambda we do have non-trivial solutions, right? Because it's not for every lambda we will always has non-trivial solution. Okay, so we have studied that. Now, so we know that. So look at this one. So we take a note. So note that x equal to plus 1 minus 1 are singular points, okay, of the Legendre equation. When written the equation in the normal form. Okay, normal form. Y double prime. Okay, the normal form. See here. And 1 minus x squared. Y prime plus lambda. And 1 minus x squared and y equals 0. Okay, so in this normal form, you can see because the leading coefficients is set to be 1, okay? And you see that, that in the denominator, x cannot be equal to plus 1 minus 1, okay? So that we call these 2 points, these 2 endpoints are single points, okay? So it's quite easy to see why we have that. But without considering in the normal form, you can see we make the Legendre equation as a Stern-Liebig equation, right? So this is the Legendre equation in this form is a special case of the Stern-Liebig equation. Okay, so now that so in this form, okay, when we look at this form, we know that P of x here appears 1 minus x squared, okay, and Q of x is 0, okay, and R of x is equal to 1, right? So we know that. Okay, and we regard them as functions on for all x in minus 1 and 1. Okay. Now we know that P of x is continuously differentiable. Right, so it's continuously differentiable. Okay. Okay, and the Q of x, Q is a zero function, or is a constant function, or continuous. Okay, continuous. So continuous on minus 1 to 1. Okay. Yeah. Maybe, okay, sorry. I must say, we know that here, so P is continuously differentiable. Okay. Q, X, P of X, Q of X, R of X are continuous. Okay, on the cross interval minus 1 and 1, and R of X is positive on minus 1 and 1. Okay, so you can see that define. Okay. Okay, so in this way, you see that when we make the general equation as a species of the Stern-Liebig equations. So you can see that P of x is continuous, differentiable. Okay, so they are all continuous. So P of x, P prime of x, Qx, Rx are all continuous functions. Okay, and the R function is positive. But how about the P function? Well, how about P function? But although P of x is positive for all x in minus 1 and 1. Okay? And minus 1 is equal to 0 equal to P1. Okay? So this is the violation. The violation of P to a regular Sturm-Liouville equation. Okay. Okay. So that and in that situation, so that's the Differential equation is a regular, it's a singular, I'm sorry. It's a singular Sturm-Liouville equation on the interval A equal to minus 1 and 1. Okay? So that, I'm sorry. So now in this form, now x in here, so we got them. All right. Defined x in this interval. Okay. Okay. All right, so we have the, we have the a singular Sturm-Liouville equations, and this is singular Sturm-Liouville equations deviate from a regular Sturm-Liouville equation only in one case, where that the P-function is not always positive in this defining interval. Okay, it is positive for all points in the defining except at the both ends. So P has 0 value when x equal to minus 1 and equal to x equal to 1. Okay, so that this violation makes this Sturm-Liouville equation singular. Okay. Okay. Now we review our result in ODE. So, for example, by the method of power series, okay, the Differential equation has a general solution. Okay, y h, because x is homogeneous linear equations. So yh is equal to c1 y1 plus c2 y2. Okay, and with y1 of x is equal to k from 0 to infinity a sub 2k and x to the 2k's power, and y2 of x is equal to summation k from 0 to infinity a sub 2k plus 1 and x 2k plus 1. Okay? So Y1 is a power series consists of even power term, and Y2 is also again a power series consists of an odd power term here. Okay, so we have so that is the general solution of the general equation, and the coefficients in the power series has the following property: A0 is equal to A1 is equal to 1. Okay, and n plus 2 is equal to n times n plus 1 minus lambda divided by m plus 1 and m plus 2 and a sub m for all m greater than equal to 0. Okay? So we can obtain the coefficient of the power series recursively applying this formula here. Okay, as you can see that. Right, so this is the homogeneous solution, general solution that we obtained by the method of power series. Okay. Now, if lambda is not equal to sum n times n plus 1, because when lambda is equal to sum n times n plus 1, now if n equal to such n, then this becomes 0. And when it's 0, by recursion, that the following coefficient come to all zeros. Okay? So that in that case, if this is equation, then the power series become to polynomial. But if lambda is not equal to any of this product, right? Then this coefficient never 0. Okay? This coefficient never 0, and so that this is indeed an infinite power series. Okay? So this is an infinite power series. Right? So if not equal for any integer greater than 0, and the y1 and the y2, okay, are infinite. Okay, are infinite series, okay, with non-zero coefficients, and have the same radius of convergence to be 1. Alright, so by the ratio test, things, alright, so when you do the ratio test, is equal to okay, so we know that. So the convergence equal to be 1. Okay, but if lambda is equal to n times n plus 1 for some integer n greater than or equal to 0, one of the two linearly independent solutions, or 1 and or 2 is a polynomial. Okay, it's a polynomial. And the other is an infinite series with non-zero coefficients, which is a radius of convergence equal to 1. Okay? Equal to 1. So a polynomial solution of the Legendre equation for the parameter lambda equal to n plus 1, it's of degree is of degree n, okay, and it's an even function when it's even, and an odd function and is odd. Okay, so we have the solution of the Legendre equations. Okay, and with the coefficients En of the highest power xn is set to this number n equal to 2n factorial divided by 2 to the nth power and n factorial and square it. Right, and this is equal to 1 times 3 times 5 times that 2n minus 1 divided by n factorial, okay, for all with equal to 1. Right, so we set the coefficient of the highest power xn to be this number, and for if n is equal to 0, if n is equal to 0, then we define it. We define 1 equal to 0. Okay. Okay. In this setting, then the Legendre polynomial Right, so the polynomial solution of the Legendre equation for the parameter lambda equal to n plus 1. Okay. Alright, so we can write it down here. T from 0 to n divided by 2. So we take this is the Gauss number. So what is the largest integer? Largest integer less than n divided by 2. Okay, and minus 1 of k, and here is 2n minus 2k factorial 2n's power k factorial n minus k factorial n minus 2k factorial x n minus 2k. Right, so this polynomial here has degree of n, and which is called Legendre polynomial of degree n. Okay, so now from here it is clear that Pn of x is continuous based on the Finnegan's interval, and then bounded. Okay, and then bounded minus 1 and 1. Okay, so very clear. The polynomial solutions of the Legendre equation is continuous on this corresponding to the interval. Okay, and so it's bounded, of course, bounded by the extreme value theorem. However, okay, any infinite series solution y of x which is equal to infinite series with only even power, or even series with odd power. Okay, so any series solution of the Legendre equation, okay, is unbounded. Okay, in minus 1 to 1. Okay, because that it will go to either infinity, right? So the absolute value of the infinite series will go to infinity when it approaches to minus 1 or 1. Okay, minus 1 or 1. And alright, so things, if you take the limit, so if x go down to minus 1, right? So if x go down to minus 1, then this go to absolute infinity. And if x go up to 1, then it's also go to infinity. Right, so you can see that infinite series solution exists in this open interval, but it is unbounded because that as x goes approach to -1 or 1, then the x value of the series sum will go up to infinity. So it will go up. Okay, so all right. So if we impose boundary conditions, okay, and two endpoints, all right, to the to this standard problem, okay, which is equivalent to the Legendre equation, but not in the normal form. Okay, just in this form. Okay, so now we have the way. Now, so since a solution, okay, U of the Legendre equation may be unbounded. Near either n point x equal to +1 or x equal to -1 or both. Okay. Alright, or both, then i.e. either the limit x to -1 plus, so that is from s going down, -1 and x or the limit x go up to 1 okay to what? Okay, ux all both are -1 or plus plus or minus infinity and integral. And integral, okay, should be, I interpret it as an improper, as okay, as an improper integral. Okay, so Okay, so it's defined to be so x epsilon positive go down to 0, 1 minus epsilon, and the minus 1 plus epsilon, you have x dx. Right? If the limit exists, okay, so that's the Lagrange identity, right? It's here, the identity minus remember that for all for the Legendre equations here, you see the Witten function R x equal to 1. Okay. So that means that because the Witten function is the constant one, it means that we don't need to wait to so that one is here. Okay. And so the Lagrange right? So that this difference it becomes 2 equals 0, 1 minus epsilon, minus 1 plus epsilon, and u x minus ux and v, okay, is equal to the limit down to 0, p of x, u prime of x, vx bar minus u of x, v prime of x bar, 1 minus epsilon minus 1 plus epsilon. Okay, so that you see that this is by definition, and okay, and this difference is equal to, this is by Lagrange equation identity here, right? So that now, so since the limit as epsilon go down to 0, p minus 1 plus epsilon. Okay, now the substitution, this is 0, is equal to the limit epsilon goes to 0, p 1 minus epsilon. So that when we do the substitution here, the p of 1 minus epsilon goes to 0 as epsilon goes to 0, and p of minus 1 plus epsilon also goes to 0 as epsilon goes to 0. Right, so that we will have that. So minus okay, so this one, because of that, so no matter what is u and v, okay, goes to 0, is 0 if we impose, so if we impose the boundary conditions, okay, that u, v, u prime, v prime are bounded. Okay, near the two end points, x equal to plus 1 minus 1. Okay, so why? Because if we know the functions are bounded, okay, then when they go to 0, then the polars goes to 0. But if they are unbounded, so it's possible this is go to infinity. So even though this is going to 0, but 0 to infinity is nothing uncertain. Okay, right? So it's important that this is what we want, right? This is what we want, and so if we impose this so-called the boundary conditions. Alright, so now this gives us a hint. So we let V sub L consist of all complex over real valued function U on minus 1 and plus 1, right, such that okay, oh, okay, now okay, in this case, so that I think I can, I still, okay, sorry, so I should keep the interval to be open. Okay, sorry. Okay, so that, alright, so we ask for complex ideal value functions on the open interval, okay, such that 1 and u x continuously differentiable on minus 1 and 1. Okay, and second, u prime is absolutely continuous on minus 1 and 1, which implies that the second derivative u double prime of x of u of x exists for almost all x in the open interval. And the third one, that U double prime is in L2 space. Okay. And the fourth, U and U prime are bounded near the two endpoints x equals +1 -1. Okay, so that we impose the boundary conditions. Okay, and it can be verified that V sub L is a vector subspace of the L2 space defined on functions defined on the open interval from -1 to 1. Okay, and then the gender still near the operator, okay, L, which send U to, right, so L is defined on V sub L, go to L2 space, with send U to what? To 1 minus S square and U prime. Okay? Because R equals 1 and Q is 0. Okay? R equals 1. Okay, R equals 1, right? Q is 0 here. Okay. Okay, so for this, the gender standard the operator, okay. Now, this operator is self-adjoint. Okay. With respect to the weighting function. Rx, which is equal to 1. So we know that it's self-adjoint. So that we have LU V here equal to, so without the index R here, it means that the weighting function is just the constant one. Okay. Okay. So we have this identity, which makes that in BL. Okay, in BL. Alright, so now, so from our previous discussions, the solutions of the Legendre equation was either a polynomial called the Legendre polynomial or an infinite series, okay? An infinite series, but as we discussed here, if the solution is an infinite series, then it would be unbounded, right? Unbounded in this interval. Okay, so that these solutions cannot be in VL. Cannot be in VL. But okay, so that lambda is an eigenvalue of the Legendre Stern-Liouville operator L, if and only if lambda must be equal to n times n plus 1 for a non-negative integer. And here. Okay? So for but in that case, we will have a solution which is just the Legendre polynomial of degree n, right? Alright, and from our discussion, each eigenvalue, n sub n, defined to be n plus 1, is non-degenerate. Okay, it's non-degenerate with a corresponding eigenfunction p sub n of x. Okay, so this one is the Legendre polynomial of degree n. Okay, now, and so if n not equal to m, the two Legendre polynomial Pn of x and p sub m of x are orthogonal, okay, over -1 to 1, i.e. Pn and Pn, which is Pn of x, Pn of x dx. So this integral must be 0. Okay, by the solve of the joint property of the Legendre Stern-Liouville operator. Yeah. Which can be proved as in theorem 11.5.1. Okay, so again, again that we have orthogonality among Legendre polynomials. Okay, so that in this sense that, okay. Okay, and so for any function in the L2 space, the series summation n from 0 to infinity Cn Pn of x with Cn, okay, which is the Pn divided by its length. Okay, so usually we just take this one, okay, and this one is 2n plus 1 divided by 2, okay, 1 minus 1 f of x and the Pn of x dx. Okay. Okay, I forgot to put this one. Okay. But remember, the Legendre polynomial has real coefficients, so that if you put the bar over there, it's the same as without putting the bar over the Legendre polynomial. Okay. So anyway, so that okay, with that, so this series, okay, is called the Fourier Legendre series. Series generated by f with respect to the eigensystem Pn of the Legendre scenario problem, and where the square of the length, of Pn, okay, as we know this is Pn in the product 1 minus 1 Pn square, and this is equal to, okay, 2 divided by 2n plus 1. Okay, 2n plus 1. By the way, I forgot to give that. This is divided by, okay, square. I'm sorry. Yeah, I forgot to put the square here. Okay, I'm sorry. Yeah, this is the square here. Okay, so so we have so this is the series we call the Fourier Legendre series generated by f. Okay, in here. Okay. So right. So once we have and note that the eigensystem is a saga but not normalized. See here. Okay. So this eigensystem we call a saga eigensystem. okay, because it is not normalized yet. Okay. Okay, so once we have for the Fourier Legendre series, now we can state the representation theorem of the Fourier Legendre series. Alright, so we let f be piecewise continuous okay. Okay. Because the system. Okay, here. Right, because the eigensystem here is polynomial, so it can be defined on the two endpoints, one minus 1 and plus 1, so that we can, in this case, we can consider functions defined on the finite closed interval, including the 2 points. Okay, that's fine. So, yeah. Okay. So we can consider a function, this one. Okay. Alright, so if f is be piecewise continuous on minus 1 and plus 1, and have left-handed, left hand, and have a left hand derivative. And right hand derivative. Okay. So maybe I'll say that have piecewise continuous derivative minus 1 and 1. Right, so we assume here, then 1, the Fourier Legendre series, okay, summation from 1 to infinity Cn being of x generated by f with respect to the orthogonal eigensystem Pn from 1 to infinity of the Legendre Sturm-Liouville operator on verse 1. Okay, will converge to the half of the left-hand limit and the right-hand limit of the f function at each point. At each point, x in the open interval, and that 2 f minus 1 plus at x equal to minus 1, and that 2 f 1 minus at x equal to 1. Okay, so this is the endpoint. Second, if in addition, okay, f(x) continuous on a subinterval I of minus 1, 1, then the Fourier Legendre series generated by f. So, so the summation from the infinity Cn Pnx converges to f uniformly on I. Okay. Alright, so the Legendre equation is an example of singular Sturm-Liouville equations, and we can still obtain an orthogonal eigensystems. Okay, and then using the orthogonal eigensystem to offer the Legendre Sturm-Liouville operator to establish the Fourier Legendre series. Okay, we can do that. And this series has this representation theorem. So the first point here is that the Fourier Legendre series will converge at every point. Okay, and if the point is in the interior point, then it will converge to the arithmetic average of the left-hand limits and right-hand limits of the function f at point x. But at the two endpoints, okay, it will converge to at the left endpoint, it converges to the right limit, right, of f at that point, and at the right endpoint, it converges to the left-hand limit at that point. Okay, so we know it's still a way behind, and this is very good for any piecewise continuous such that has a piecewise continuous derivative. Okay, on this finite closed interval. And we also have uniform convergence of the Fourier Legendre theories if the function, the original function f is continuous on a subinterval of this open intervals. Okay, so we have that. So this is uniformly. Okay, so this is the first, and it's very important. Singular standard problem. The other important singular standard problems is corresponding to the Bessel functions, Bessel equations we studied in the ODE. Okay, so let's take a look at. Right? So we consider the Bessel equation of order mu going to equal 0. Okay. Now, so we write the Bessel equation. Okay. As a standard equation here. Okay. Right, and we confine the defining interval to be an open interval from 0 to b. Okay, and b is something predetermined, okay? Or lambda is a parameter. Okay. And here, if we rewrite the Bessel equation in a normal form, so we know that x equals 0. It's a singular point of the Bessel equation. Okay, when written in the normal form. Y double prime plus 1 over x y prime plus minus nu square x square plus lambda and y equal to 0. Okay, now so we look back to the Bessel function written as standard equations here. Now we know that p of x is equal to x, okay, and q of x is equal to minus nu square and x. All right, and we know r of x, the r of x is x here. Okay. X. Right. So we know p of x is continuously differentiable. Okay. Everywhere, right? And r of x is continuous on 0b. Okay, and P of x will be 0, I of x will be 0, 0 to b. Okay, so it's positive, except, okay, I'm sorry, including b. So in this interval, the p of x, right, and Rx are all positive, no problem with that. Okay, and R of x is also continuous, right? So it's equilibrium. This R of x is x. And but although Q of x is continuous, okay, 0b here. This is left open and right closed, but it is unbounded. Okay, so it's unbounded near the endpoint x equal to 0. And also, we know that P0 equal to R0, okay, equal to 0. Okay, so that's the basic equation is a singular stem linear equation on the interval I is b. Okay, so this is so in this interval, half open, half closed interval, this special equation is actually a singular stem linear equation. Okay, so that to establish, okay, we should imposing suitable boundary conditions, okay, for the solutions of these special equations, so that the corresponding stem linear operator, okay, becomes to be self-adjoint. Okay, all right. So the procedure will follow the procedure we have done for the gender equations. Okay, and so I will not go through the detail, because that we should discuss the solution of the basic equations. Okay, the discussion of basic equations. All right, and so because time is very limited, so that I have actually read the material in the lecture notes. Okay, so I will ask you to read the lecture notes. Of course, I should send the lecture notes as soon as possible to you. All right. Okay. All right. Okay. So I have to say here. For the for establishing orthogonal meaning to now the basal stream behavior problem. Right? Please see the lecture notes. Okay? So you have to read the lecture notes to understand that the process that how we establish and also Gardner eigensystems for the basal stream behavior problems. Okay, and there we will impose proper boundary conditions, just like for the gender stream behavior operator. In this case, the imposing boundary condition would be that they should be bounded near the two endpoints. Okay, so of course we should impose some special boundary condition at the endpoint 0 here. Okay, all right. So now so we will have and the detailed discussion will be in the lecture notes. Okay, and so we will so we see that we have complete the section number 5 on the stream behavior problems. And so the next lecture I will start with section number 6. Okay, and because that next Tuesday is a national day, so it's a holiday, and so I will record an online lecture, and so you can watch the recorded lectures, okay, in my YouTube channel. Okay, and so the TA will let you know when it is ready for you. Okay, so I'll stop here.